The model can dream, but it cannot do. It completely lacks the functional calling capabilities and the autonomous execution loops necessary to interface with a booking API. Check a Boolean availability flag and reserve the room. That is the execution gap in a nutshell.
It is. But the architectural failures compound significantly when we examine the learning gap. The sources detail a much higher stakes scenario involving Dr. Jessica, a climate researcher, preparing a critical presentation for a UN summit.
Right, this one is terrifying from a data integrity perspective.
It really highlights a fundamental vulnerability in utilizing stateless LLMs for rigorous data analysis. Dr. Jessica had to step away due to an emergency, leaving her postdocs to complete a comprehensive analysis of global food security datasets using generative AI.
And when she returned to review the findings prior to her keynote, the team presented her with highly compelling, beautifully formatted narratives regarding climate impacts on specific agricultural yields.
The problem, of course, surfaced during the verification phase. When Dr. Jessica checked the academic citations provided by the model, they returned HTTP 404 errors or simply didn't exist in any academic database.
The model had hallucinated the citations.
It had. But the more insidious issue was what the authors referred to as a lack of coherent persistence. The research team had utilized multiple concurrent chat sessions to process different subsets of the data.
And because standard generative AI architecture does not maintain a persistent logical state or long-term memory across isolated sessions, the model began outputting mutually exclusive statistical claims.
Exactly. It would generate one set of crop yield metrics in session A and confidently state completely contradictory metrics in session B.
Because a transformer model is designed to predict the next most likely token based purely on the immediate context window provided to it, it does not contain an internal verifiable relational database of facts.
It prioritizes semantic coherence, sounding like a highly confident, articulate human over strict verifiable accuracy. If it doesn't know a fact, the mathematical weights will often push it to invent a highly plausible-sounding string of text to complete the pattern.
And without a continuous memory architecture to ground its outputs against past interactions, it cannot self-correct across sessions. For anyone designing enterprise infrastructure, deploying an ungrounded, stateless, probabilistic model into an environment that requires absolute data integrity is a catastrophic architectural choice.
Absolutely catastrophic. But the most critical system failures occur within the third category, the coordination gap. The text examines a scenario involving a patient, Maria, arriving at a general hospital emergency room.
The hospital in this scenario has actually invested heavily in digitalization, right? They have deployed specialized narrow AI systems across various departments.
Correct. So Maria presents with severe abdominal pain. The hospital's natural language processing intake system correctly analyzes her symptoms and medical history, flagging a high probability of post-surgical complications from a recent procedure.
So the individual nodes in the network are actually performing optimally.
Yes. The continuous monitoring system detects a sudden drop in her blood pressure. The automated laboratory analysis system flags specific biomarkers indicating potential internal hemorrhaging. The pharmacy system cross-references her current medications and flags a high-risk contraindication with standard emergency pain management protocols.
You have multiple, highly sophisticated diagnostic engines independently arriving at correct conclusions regarding a life-threatening multivariable emergency.
Yet, because these systems exist in siloed architectures, they cannot coordinate a unified response. The laboratory system cannot trigger a halt in the pharmacy system. The intake system cannot dynamically adjust the polling rate of the vitals monitor based on its initial hypothesis.
So the burden of coordination falls entirely on the attending nurse.
Entirely. The nurse must manually poll the dashboard of the vital system, switch context to the laboratory portal, mentally synthesize the disparate data streams, recognize the emerging pattern, and manually input the synthesized data into the electronic health record to trigger the hospital's emergency intervention protocol.
Precious time is consumed because the digital infrastructure lacks an orchestration layer.
If we connect this to the bigger picture of enterprise digitalization, this is the ultimate manifestation of the integration crisis. The human operator is utilized as the data bus, connecting incompatible software components.
This represents a structurally broken architecture. Scaling an enterprise cannot rely on human cognitive overhead to patch the communication protocols between isolated AI insights.
The future of robust enterprise architecture requires systems capable of proactive state monitoring, autonomous inter-system API communication, and the execution of asynchronous multi-step processes without human intervention acting as the middleware.
So the architectural challenge is incredibly clear. How do we transition from these siloed passive systems to an integrated active architecture? How do we take the cognitive reasoning capabilities of a large language model and wire it into the digital infrastructure so it can manipulate state?
The source material frames this evolution through the concept of the digital worker, introducing the SPAR framework and the Agentic AI progression model.
To understand the architecture, we first have to standardize the terminology. The term agent is derived from the Latin agere, meaning to do or to act. In this context, an AI agent is fundamentally distinct from a prompt response chatbot.
Right, a chatbot is a one-shot process. Input string in, output string out. An agent is a continuous autonomous system operating on a feedback loop. The authors formalize this as the SPAR framework, sense, plan, act, and reflect.
When you look at the SPAR framework, the parallels to control theory and the operational loops of autonomous vehicles are immediately apparent.
The analogy is highly instructive for understanding the system architecture. Let's break down the sense phase. In an autonomous vehicle, the system relies on physical sensors, LiDAR or raised radar, and optical cameras to ingest real-time environmental data.
Right, it has to see the road.
For a digital AI agent, the sense phase involves ingesting state data from the digital environment. This is accomplished through API polling, listening for specific webhooks, executing SQL queries against databases, or parsing unstructured data streams from email servers or Slack channels. The agent is continuously maintaining an internal state representation of its digital environment.
And once the state is ingested, the system moves to the plan phase.
In the vehicle, the onboard compute cluster calculates the optimal trajectory, adjusting for obstacles in traffic flow. In an AI agent, the plan phase leverages the inferential capabilities of the large language model. The LLM processes the ingested state data against its programmed objective.
It breaks the overarching goal down into a directed acyclic graph or a step-by-step logical sequence.
Exactly. It evaluates different potential API calls, weighs the likelihood of success for each, and generates an execution strategy.
Following the plan is the act phase. The self-driving car translates its trajectory calculations into physical actuation, adjusting the steering column or applying brake pressure. The digital agent translates its plan into digital actuation.
It executes a post request to an external API, commits a write operation to a database, triggers a script, or generates an outbound communication.
And the final phase, which is arguably the most critical for an autonomous system, is reflect.
After the vehicle adjusts its steering, it immediately polls its sensors again to verify if the physical outcome matches the intended trajectory. If it is drifting, it calculates a correction.
Similarly, after the digital agent executes an API, call it must parse the response. Did the server return a 200 OK status or a 403 forbidden? If the action failed, the agent feeds that error log back into its context window.
It uses the LLM to analyze the failure, adjust its internal plan, and reattempt the task using an alternative method. This continuous asynchronous SPAR loop is the defining architectural characteristic of an agentic system.
To contextualize where current enterprise systems sit within this paradigm, the authors detail the Agentic AI progression framework. It outlines 5 distinct levels of autonomy, purposefully mirroring the SAE levels of driving automation.
Understanding these levels is critical because selecting the wrong architectural level for a specific business process can lead to, for example, a level 2 system might use a trained computer vision model for optical character recognition to extract invoice numbers from scanned PDFs and then feed that extracted string into a deterministic RPA script for routing.
Both level 1 and level 2 are fundamentally deterministic. They run on tracks. The system executes exactly what is explicitly programmed and nothing more. If an exception occurs that falls outside the hard-coded logic tree, the process halts and throws an error to a human.
But the paradigm shift occurs at level 3 agentic workflows. This is the current frontier of enterprise AI integration.
Level 3 represents the transition from deterministic scripts to probabilistic systems powered by large language models. To extend the transportation analogy, if level 2 is a train on fixed tracks, level 3 is an autonomous taxi navigating a city.
The taxi understands the ultimate objective, transporting the passenger to a specific coordinate. If it encounters a blocked intersection, it doesn't just halt and wait for a human to rebuild the road. It uses its internal map to dynamically calculate an alternative route, navigating the obstacle autonomously.
In a digital context, a level 3 agent utilizes the LLM as its reasoning engine to navigate digital obstacles. If it attempts to pull data from a primary API and receives a timeout error, it can reason that it needs the data to proceed.
It can identify a secondary database holding cached data, formulate a SQL query, extract the data, and continue the workflow.
The agent leverages the entire SPAR framework to handle edge cases without explicit pre-programming for every possible failure state. Level 4 semi-autonomous and Level 5 fully autonomous represent future architectural states.
Level 4 systems will dynamically learn and optimize their workflows across complex domains with minimal human oversight, while Level 5 systems theoretically represent general-purpose agents capable of executing any digital task continuously self-improving without human intervention.
But the authors emphasize a critical architectural principle here. Just because Level 3 is the cutting edge does not mean it is the appropriate solution for every problem. They introduce what they call the golden rule of AI agents to deploy the simplest system necessary to achieve the objective.
This is a fundamental concept in systems engineering. Complexity introduces latency, increases compute costs, and widens the surface area for failure.
If you are architecting a system to perform highly sensitive, strictly regulated compliance checks, where the penalty for error is severe, you do not want a probabilistic Level 3 agent involved.
An LLM's capacity for dynamic reasoning is inherently tied to its capacity for hallucination or unexpected deviation. For mission-critical, low-variance tasks, the rigid, absolute determinism of a Level 1 or Level 2 system is vastly superior. You must align the autonomy level with the risk profile and structural demands of the specific workflow.
Here's where it gets really interesting, though. How do we actually build a Level 3 system? How do we take a transformer model, which is fundamentally designed to intake a sequence of tokens and output the statistically probable next tokens and wire it up so it can interact with a production database?
This brings us to the core technical architecture of the book, the 3 keystones of agentic AI. These keystones are action reasoning and memory.
Let's drill down into the first keystone, action. How do we give the AI its digital hands?
An AI agent bridges the gap between probabilistic text generation and deterministic system execution, primarily through 3 interaction vectors. System controls, which involve utilizing libraries to simulate physical keyboard and mouse events, direct database connections, allowing the agent to execute SQL or NoSQL queries, and most importantly, APIs.
And the underlying technical breakthrough that enables a large language model to reliably interface with an API is a capability known as function calling.
Function calling is the linchpin of modern agentic architecture. Before this capability was natively integrated into models, developers had to rely on highly fragile prompt engineering.
You would prompt the LLM instructing it to output a specific text string like action get weather location, London, and then you would have to write complex regular expressions on your application backend to parse the LLM's raw text stream, extract those variables, and pass them to your API.
It was prone to formatting errors and required constant maintenance. Function calling fundamentally changes how the model interacts with external tools. In a modern architecture, the developer defines a strict schema of available tools, usually formatted as a JSON array, and injects the schema directly into the model's system prompt or specialized API parameter.
This schema acts as a highly structured API contract. It tells the LLM here is a tool called fetch customer data. It requires a string parameter called customer ID and an optional Boolean parameter called include purchase history.
When the user asks the agent a question the LLM processes, the natural language evaluates its available tools and determines if it needs external data to fulfill the request. If it does, it halts its standard text generation process.
Instead, it generates a highly structured JSON payload that perfectly matches the required schema.
The application layer intercepts this JSON payload. The LLM itself doesn't make the HTTP request your application backend takes that perfectly formatted to city. JSON executes the actual fetch customer data API call, receives the response from your database formats that responds back into a text string, and injects it back into the LLM's context window.
The LLM then reads the data and generates the final natural language response for the user. It is a highly elegant bridge that forces a probabilistic model to communicate in strict deterministic data structures.
The source material raises an interesting behavioral distinction regarding how agents utilize these tools compared to humans. Human intelligence is characterized by creative repurposing. If a human needs a paperweight and only has a hammer, they will intuitively use the hammer as a paperweight.
But an AI agent operates with rigid, defined utility. If you provide an agent with an API to send an email, it will only ever conceptualize that tool as a mechanism for sending emails.
From an enterprise engineering standpoint, that strict limited utility is exactly what you want. You're building systems for operational predictability, not abstract creativity. You need absolute certainty regarding how a specific tool will be utilized by the autonomous system.
However, building an architecture entirely dependent on external API calls introduces significant vulnerabilities. Network latency spikes, third-party APIs deprecate endpoints, and servers experience downtime.
This necessitates what the authors define as the tool resilience framework.
The tool resilience framework is essentially a risk management matrix for API integration. It plots every tool available to the agent on two axes, the likelihood of disruption against the importance to the mission.
Exactly. If a tool falls into the quadrant of low importance and high likelihood of disruption, perhaps an API that fetches real-time sentiment analysis from social media for a marketing agent, it can be treated as an optional parameter.
If the API fails, the agent logs the error and proceeds with the workflow using historical data.
But if a tool is designated as high importance and high likelihood of disruption, such as a legacy on-premise inventory database that frequently experiences micro-outages, the engineer must design robust fallback architectures within the agent's logic.
You can't just let the workflow crash. The agent must be programmed with graceful degradation protocols. If the primary inventory API times out after 3 attempts, the agent's logic tree should automatically redirect its query to a read-only Redis cache.
Or failing that, execute an escalation protocol to alert a human operator, providing them with the exact state of the workflow at the point of failure.
Furthermore, integrating an autonomous agent with production tools requires strict adherence to the principle of progressive access. You do not provision a newly deployed agent with administrative right privileges across your enterprise ecosystem.
The implementation must follow a zero-trust model. You start by provisioning the agent with read-only access. You deploy it in a shadow capacity, allowing it to run its SPAR loops and generate its JSON payloads based on live data, but preventing it from actually committing any state changes.
You meticulously log its decision trails, analyze its error rates, and verify that its API calls are correctly structured.
Only when the system has demonstrated statistical reliability over a significant sample size do you begin progressively elevating its permissions, granting write access to low-risk peripheral systems before ever allowing it near core production databases.
So we have established the action keystone, the mechanisms for manipulating the digital environment. But action without logical intent is just chaotic execution. This leads us to the second keystone reasoning.
How do we shift the LLM from merely generating fast text to executing deliberate, complex problem-solving?
This requires understanding the cognitive modes of the underlying models. Generative AI natively operates using what cognitive psychology refers to as System 1 thinking. It is highly intuitive, associative, and near instantaneous.
When you feed a prompt into a standard model, it processes the tokens through its neural network layers and immediately begins outputting the most statistically probable response. It does not pause to evaluate multiple hypothetical scenarios.
But enterprise workflows rarely resemble simple trivia questions. They require System 2 thinking, deliberate, methodical, logical planning. They require the ability to break a complex problem into subtasks, execute a task, evaluate the outcome, and adjust the strategy based on the new information.
The authors illustrate this distinction with the analogy of solving a complex crossword puzzle. When a human attempts a crossword, they do not simply look at the empty grid and instantaneously stream the correct letters into every box in a single, uninterrupted flow of consciousness.
The human approach is highly iterative. You analyze the board, identify the most constrained areas, and formulate a hypothesis for a specific word.
You mentally test that word, realizing that if you use it, the third letter creates an impossible constraint for a vertical clue. You discard the hypothesis, formulate a new one, write it down, and use that newly established baseline to attack the next clue.
You are constantly interleaving reasoning, action, and observation. To force LLMs into this System 2 modality, researchers developed a prompting framework known as REACT, short for reasoning and acting.
The REACT framework is a massive leap forward in agentic design. Instead of prompting the model to simply provide an answer, you explicitly instruct the model to output its internal thought process.
The model generates a structured output consisting of 3 distinct phases: thought, action, and observation. First, it outputs a thought trace detailing its logical rationale for the next step. Then, it outputs an action generating the JSON payload to call an API.
The system executes the API and returns the result, which becomes the observation. The model then begins the loop again, generating a new thought based on the observation.
By forcing the model to articulate its logic before generating an action command, you drastically reduce the probability of hallucination or illogical execution. The text generation itself becomes the computational workspace where the model organizes its logic.
This methodology has proven so effective that the latest generation of models, such as OpenAI's O1 and O3 series, are explicitly trained using reinforcement learning to optimize these internal reasoning traces natively.
And this introduces a profound shift in the economics and architecture of AI compute. Historically, the prevailing scaling law dictated that model performance scaled linearly with the amount of training data and the sheer volume of compute utilized during the pre-training phase.
You want a smarter model, feed it a larger data set, and train it on a larger cluster of GPUs for a longer duration.
But the focus on reasoning has revealed a new scaling law, inference time scaling. Performance scales dramatically based on the amount of compute you allocate during the inference phase the moment the user asks a question.
Exactly. Instead of demanding an instantaneous response, you allow the model to spend significantly more time thinking. It runs extensive hidden chains of thought. It generates multiple potential execution paths, tests them in isolated logical sandboxes, critiques its own logic, discards failed branches, and only outputs the final result after it has thoroughly verified the logical integrity of its plan.
From an architectural perspective, we are trading raw latency, the speed of the initial token generation, for massive increases in complex reasoning fidelity. You might wait 30 seconds for an agent to respond, but the resulting action plan will be vastly superior to an immediate System 1 guess.
So the agent has the tools to act and the logic to reason. But neither of these keystones are effective if the system suffers from digital amnesia. A brilliant planner that forgets the entire context of the project every time it switches tasks is useless.
This brings us to the third keystone: memory, building coherent persistence into the architecture. As we analyze in the Dr. Jessica case study, the baseline architecture of a transformer model is stateless.
It only remembers the specific tokens contained within its immediate context window. Once that context window limit is reached, older tokens are truncated, and the model literally forgets the beginning of the conversation.
To construct a highly functional Level 3 agent, engineers must build an externalized long-term memory architecture that the agent can read from and write to continuously. The source material categorizes this long-term memory into 3 distinct architectural layers.
For an engineer designing these systems, understanding how to build and integrate each layer is crucial. The first layer is episodic memory.
Episodic memory provides the agent with chronological context. It stores the specific history of interactions, past events, and state changes. If a user interacts with a customer support agent on Tuesday, the agent needs to recall the exact parameters of that interaction when the user returns on Friday.
Architecturally, episodic memory is typically managed using highly structured relational databases, SQL tables that log timestamps, user IDs, session metadata, and discrete action logs. It ensures the agent maintains continuity of experience across asynchronous sessions.
The second layer is semantic memory. This is where we move away from structured logs and deal with the vast domain of unstructured knowledge.
Semantic memory stores the facts of the world, product specifications, corporate policies, historical data, and general domain knowledge. You cannot fit a 1,000-page corporate compliance manual into an LLM's context window for every single prompt.
Instead, we utilize an architecture known as retrieval augmented generation, or RG, powered by vector databases. The mechanics of RAG are essential to understand.
When you build a semantic memory layer, you take your unstructured data, say a massive repository of PDF technical manuals, and you run it through an automated chunking process. You slice the documents into overlapping segments of text, perhaps 500 tokens each.
You then pass each chunk through an embedding model which translates the semantic meaning of that text into a dense, high-dimensional numerical array or a vector. You store these vectors in a specialized database like Pinecone or Milvus.
When the agent encounters a situation requiring factual knowledge, it takes its current thought trace and runs it through the same embedding model, converting its query into a vector.
The database then performs a mathematical operation, typically a cosine similarity search, to find the vectors in the database that are closest in multidimensional space to the query vector.
It retrieves the original text chunks associated with those nearest vectors and dynamically injects them into the LLM's prompt window.
The agent is essentially performing a highly precise semantic search against its own internal knowledge base in real time, fetching only the specific facts it needs to complete its reasoning loop, completely bypassing the limitations of the fixed context window and massively reducing the probability of hallucination.
Because the model is generating answers based on retrieved, verified data rather than its internal statistical weights. The third and final layer of the memory architecture is procedural memory.
This layer stores the how-to knowledge. It contains the codified workflows, the decision trees, the compliance protocols, and the specific step-by-step logic required to execute enterprise processes. If an invoice exceeds $10,000, what is the specific chain of API calls required to trigger executive approval? That logic resides in the procedural memory.
The book provides a compelling example of how a dynamic memory architecture transforms an agent into a compounding asset. A European automotive parts manufacturer deployed a specialized AI agent to oversee quality control on a physical assembly line.
The agent utilized computer vision models to inspect manufactured components for microscopic defects. Initially, the agent's procedural memory parameters were too rigid, resulting in a high rate of false positives, flagging acceptable parts as defective.
In a traditional deterministic system, a software engineer would have to manually analyze the logs, adjust the pixel tolerance thresholds in the code, recompile, and redeploy the update.
But in an agentic system with dynamic memory, the architecture handles the optimization. When the human quality control inspectors overruled the agent's false positives, that specific feedback loop was captured.
The system encoded the visual data of the corrected part alongside the human's ruling and wrote it back into the agent's semantic and procedural memory layers. The agent autonomously updated its internal parameters for what constituted an acceptable variance.
By continuously integrating real-world feedback into its persistent memory, the agent reduced its false positive rate by 40% over a short operational period. It wasn't just executing a static script, it was actively learning and refining its operational logic.
That is the realization of coherent persistence. The agent becomes a continuously optimizing node within the enterprise infrastructure. So we now have a comprehensive understanding of the individual components. We have the LLM reasoning engine, the function calling action mechanisms, and the layered memory architecture.
The engineering challenge now shifts from component design to system orchestration. How do you assemble these disparate elements into a secure, scalable, enterprise-grade deployment? Now that we have the components, action, reasoning, and memory, how do we assemble them into an enterprise-grade system?
This transition brings us to part 4 of our analysis, orchestrating the system. The authors introduce a comprehensive lifecycle methodology they call the agent framework. It provides a structured approach for engineering and deploying these complex systems.
Let's walk through the architecture of this framework. The A stands for agent identity. Before you write a single line of code, you must explicitly define the persona, the operational boundaries, and the specific objective of the agent.
Is it a highly conservative compliance auditor or a creative marketing assistant? Defining the identity dictates the system prompts and the tonal parameters of the LLM.
The G represents gear and brain. This is the hardware and model selection phase. An engineer must evaluate the latency and compute trade-offs. Does this specific task require the massive reasoning capabilities and high token cost of a GPT-4 class model, or can it be executed faster and cheaper using a smaller, fine-tuned, open-weight model like Llama 3 running on local infrastructure?
Furthermore, you must define the exact gear, the specific schema of API tools the agent will be authorized to access.
The E is execution and workflow. This involves mapping the complex transverse workflows the agent will navigate. What are the specific digital triggers that wake the agent up? What are the required data inputs? And what are the strictly defined JSON output formats it must generate to pass data to the next stage of the pipeline?
The N stands for navigation and rules. This is arguably the most critical engineering phase, focusing heavily on security guardrails, access control, and failure routing. We'll delve deeply into the specific mechanisms for this shortly.
And finally, the T is testing and trust. Because agentic workflows utilize probabilistic models, traditional unit testing is insufficient. You cannot simply assert that input A will always equal output B.
Engineers must build comprehensive evaluation frameworks utilizing secondary LLMs to automatically generate thousands of edge case scenarios and adversarial prompts to test the agent's logic boundaries in a sandboxed environment before ever considering a production deployment.
But within this orchestration framework, the authors highlight a massive architectural paradigm shift. As developers began building these systems, they quickly realized that trying to construct a single, omnipotent Level 3 agent capable of handling an entire enterprise workflow was a disaster.
The architecture is moving decisively away from monolithic AI design toward what is known as multi-agent systems. This shift perfectly mirrors the historical evolution of software architecture, moving from massive, tightly coupled monolithic applications toward distributed microservices.
If we connect this to the bigger picture, the guiding principle for agentic design is one agent, one tool, or at least one highly restricted domain. The necessity for this shift is driven by a phenomenon the authors define as the agent's dilemma.
The core strength of an LLM is its inferential reasoning, its ability to creatively connect disparate concepts. But when you give a single agent access to 50 different API tools and a massive complex objective, that same creativity becomes a liability.
The agent might hallucinate a connection between the HR database API and the external social media posting API, resulting in highly unpredictable, potentially catastrophic behavior. The surface area for logical failure is simply too vast.
To mitigate the agent's dilemma, engineers build microservices. You compartmentalize the workflow into highly constrained, isolated agents. The book provides a clear architectural example involving the automation of a corporate intelligence newsletter.
Rather than building one massive newsletter agent and giving it unfettered access to search engines, internal databases, and the corporate email server, the developers architected a coordinated swarm of 4 specialized agents.
First, they deployed a search agent. This agent's identity and system prompt were strictly focused on information retrieval. Its gear consisted of exactly one tool, a web scraping API. Its procedural memory dictated strict search parameters regarding specific industry keywords. It executes its searches, gathers the raw text data, and its workflow terminates.
It then passes that raw payload to the second microservice, the summarization agent. This is where the security boundaries become apparent. The summarization agent has zero access to the internet. It has no API tools.
Its only function is to ingest the massive text block provided by the search agent, apply a highly specific prompt template to extract key insights, and output a condensed text string.
By isolating the summarization logic from the web access logic, you completely eliminate the risk of the model hallucinating a search query while trying to write the summary. The workflow then hands off to the formatting agent, which takes the summarized text and structures it into HTML and CSS suitable for an email client.
And overseeing this entire pipeline is the manager agent. The manager agent acts as the orchestration layer. It does not execute the distinct tasks. It monitors the state of the workflow, ensures that JSON handoffs between the subordinate agents are properly formatted, verifies that the final HTML payload meets the structural requirements, and ultimately presents the finished product to a human supervisor for final approval and deployment.
This modular multi-agent architecture is infinitely more stable, drastically easier to debug. If the formatting breaks, you only have to check the logs of the formatting agent, and it's highly scalable.
The power of multi-agent architectures extends beyond simple pipeline orchestration. It can fundamentally enhance the reasoning capabilities of the system. The source material references a fascinating study conducted by researchers at the University of Montreal. They were attempting to solve highly complex mathematical and logical reasoning tasks.
The traditional approach would be to route the problem to the largest, most computationally expensive state-of-the-art model available and hope it calculates the correct answer in a single pass.
The researchers took a different architectural approach. They utilized a panel of smaller, medium-capacity, open-weight models. They architected a multi-agent debate system. They gave the complex problem to multiple instances of the smaller models simultaneously.
Each agent generated its own internal chain of thought and arrived at a preliminary answer. Then, the orchestration layer forced the agents to share their reasoning traces with one another.
The agents were prompted to act adversarially. Agent A was instructed to actively critique the logical steps of Agent B, searching for calculation errors or hallucinations. If Agent A found a flaw, it generated a critique and fed it back into Agent B's context window.
Agent B was forced to either defend its logic or update its answer based on the new constraints. The orchestration system required them to iterate through this debate process until a consensus threshold was reached.
The results were striking. The multi-agent debate architecture, utilizing smaller, less capable individual models, actually outperformed the single massive state-of-the-art model operating in isolation.
By forcing the system to structurally interrogate its own logic, cache its own hallucinations, and dynamically refine its reasoning pathways, the architecture compensated for the probabilistic weaknesses of the underlying models.
For an engineer designing enterprise systems, building these multi-agent architectures requires rigorous attention to the N in the agent framework navigation and rules. When you have multiple autonomous nodes interacting asynchronously, you must engineer robust fail-safe guardrails.
The source material specifically emphasizes the implementation of circuit breakers. The concept is borrowed directly from electrical engineering. A physical circuit breaker trips and severs the connection when it detects a catastrophic surge in current preventing the house from burning down.
In agentic architecture, a digital circuit breaker trips when it detects a system caught in an infinite error loop. Because agents operate on the SPAR loop, reflecting on errors and trying again. A poorly designed agent can become trapped.
If an API endpoint is down and returning a 500 internal server error, a level 3 agent might rapidly generate 50 slightly varied JSON payloads in a frantic attempt to find a successful query format.
This can result in localized denial of service attacks on internal databases or rapidly drain allocated compute budgets. The engineer must program strict state machines governing the agent's retry logic.
If the agent encounters 3 sequential failures on a specific API called the circuit breaker trips, the system forcibly halts the agent's SPAR loop, logs the exact error state, and routes an escalation alert to a human developer.
Alongside circuit breakers, the architecture must mandate absolute transparency through decision trails. This is non-negotiable for enterprise compliance. Because Level 3 systems utilize probabilistic LLMs, the exact reasoning behind a specific action can be opaque.
If an autonomous agent integrated into a financial system denies a user's loan application, a human auditor will eventually ask why that decision was made. You cannot simply say the neural network weights determined it.
Exactly. The system architecture must dictate that every time an agent executes a state-changing action, it synchronously writes a comprehensive log to an immutable database. This decision trail must include the precise trigger that initiated the workflow, the specific data it retrieved from its memory architectures, the step-by-step chain of thought generated by the reasoning engine, and the exact JSON payload transmitted to the API.
The system must be capable of producing a human-readable audit trail, proving that the agent adhered to the established procedural memory rules. So we've built the architecture. We have the keystones, we have the agent framework, and we understand the multi-agent microservice topologies. How are massive enterprises actually deploying this at scale today?
This transitions us into Part 5, Enterprise Transformation and the New World of Work. The goal of digitalization is no longer simply automating isolated atomic tasks like extracting data from an invoice. The goal is orchestrating end-to-end transverse workflows.
A transverse workflow is a macro process that crosses multiple departmental silos and technology stacks. We're talking about automating the entirety of a procure-to-pay pipeline, or the complete order-to-cash cycle from the moment a customer clicks buy to the final reconciliation of the ledger.
The source material provides a deeply technical case study detailing the transformation of a massive UK retail operation called Pets at Home. Pets at Home is a perfect example of enterprise scaling because they didn't attempt to build Level 3 multi-agent systems on top of a crumbling foundation.
They recognized a fundamental truth of digitalization. Your AI agents are only as capable as your data infrastructure allows them to be.
You cannot deploy dynamic autonomous agents if your enterprise data is locked in siloed batch process systems. Pets at Home undertook a massive infrastructural modernization effort before they deployed a single agent.
They migrated away from legacy IBM mainframes and fragmented on-premise databases, consolidating their entire operational data structure into a unified real-time Azure data lake. They built a clean, centralized, accessible data environment.
Once the data infrastructure was sound, they began deploying multi-agent systems. But they didn't try to automate their entire supply chain on day one. They targeted highly specific, high-value, high-friction processes such as profit protection and identifying anomalies related to stolen goods within their logistics network.
They utilized low-code orchestration platforms to build these systems. This is a critical point for enterprise scaling. You don't want your core software engineering team spending months hard-coding custom Python scripts for every internal workflow.
Low-code platforms act as the integration layer, providing pre-built API connectors, visual workflow designers, and built-in state management. The engineers configure the agentic architecture, define the tool schemas, and connect the LLM reasoning nodes using these visual environments.
By starting small and utilizing scalable platforms, Pets at Home proved the operational value, built institutional trust in the technology, and rapidly expanded the deployment. The case study notes that today they have sophisticated agent-to-agent autonomous communication occurring continuously within their back-office processes, resolving complex logistical anomalies entirely without human intervention.
But achieving this level of digitalization forces a massive structural shift in the human workforce.
Yeah.
You're deploying digital workers capable of executing complex tasks. The human role must adapt. The authors introduced the AI Agent Collaboration Capability Model, or AICCM.
The core tenet of this model requires shifting the workforce paradigm from task thinking to workflow thinking. Historically, enterprise value was derived from employees executing specialized tasks. An accountant was valued for their speed and accuracy in reconciling specific ledger entries.
But if a procedural memory agent is executing the reconciliation instantaneously via API, calls the human's value proposition fundamentally changes. The human operator transitions from a task executor to a workflow architect and manager.
Employees are not being replaced by level 3 agents. They are being elevated to supervise a team of digital workers. To be effective, the human must understand the end-to-end transverse workflow.
They must know how the data moves from the intake system through the evaluation agents and into the final database. They become responsible for designing the system prompts, monitoring the circuit breaker logs, and handling the highly complex strategic exceptions that fall outside the agent's procedural boundaries.
To manage this massive operational and cultural transition, the source material advocates for a highly structured progressive autonomy model. You do not achieve enterprise scale by deploying a multi-agent system into production and simply flipping a switch to fully autonomous.
Trust in an autonomous system must be mathematically and empirically earned, not blindly given. The progressive autonomy model dictates starting with maximum visibility and minimum autonomy. You deploy the multi-agent system in a human-in-the-loop configuration.
The agents execute their SPAR loops, pull the data, and formulate the plan, but the execution phase is hard-stopped. A human operator must review the agent's decision trail and explicitly click an approve button before the API call is fired.
You run the system in this mode for thousands of cycles. You analyze the logs. If the agent's proposed actions align perfectly with the human's decisions 0.9% of the time, you cautiously graduate the system to human on the loop for low-risk tasks.
The agent executes autonomously, but broadcasts a real-time log of its actions to a dashboard, allowing a human to monitor the flow and intervene if necessary.
Over time, as the system continually demonstrates reliability, handles edge cases gracefully, and respects its circuit breakers, you systematically strip away the human intervention layers.
Eventually, the system achieves level 3 autonomy within its tightly defined domain, only surfacing alerts when it encounters a true, unresolvable anomaly. This progressive scaling is the only secure methodology for integrating autonomous code into mission-critical enterprise environments. So what does this all mean? We have covered an immense amount of architectural ground today. Let's do a rapid technical recap. We diagnosed the integration crisis, the limitations of stateless generative brains in a jar, and explored how the SPAR loop provides the continuous feedback mechanism required for autonomous execution.
We analyzed the shift from deterministic level 1 automation to probabilistic level 3 agentic workflows. We deeply unpacked the 3 keystones granting the system digital action through structured function calling and forcing system 2 logic, through inference time scaling and React prompting and grounding the model in reality, using layered long-term memory architectures like vector databases and RA.
Finally, we explored how the agent framework guides the deployment of multi-agent microservices secured by circuit breakers and immutable decision trails to orchestrate transverse enterprise workflows.
It is a comprehensive blueprint for engineering the next decade of enterprise IT. But this raises an important question regarding the ultimate macroeconomic implications. We've spent this entire discussion focusing on how agents will optimize internal corporate infrastructure. But the authors briefly extrapolate toward a concept that pushes the boundaries of digitalization far beyond internal efficiency: the emergence of the agent-to-agent or A2A economy.
The A2A economy. This is where the architectural models we've discussed intersect with global network dynamics.
Consider the logical progression of these systems. We are rapidly approaching a reality where your company's level 3 procurement agent, continuously polling internal supply chain databases, autonomously detects a projected shortfall in a critical manufacturing component. It does not generate an alert for a human buyer.
Instead, it formulates a procurement plan, structures a query, and reaches out across the external network to interface directly with the sales agents of multiple global vendors.
These are autonomous systems operating with massive procedural memory regarding corporate pricing strategies and semantic memory regarding geopolitical shipping constraints, communicating directly via structured APIs.
They negotiate pricing tiers, debate delivery SLAs, and verify quality control parameters, dynamically evaluating hundreds of permutations in milliseconds. Once the multi-agent negotiation reaches an optimal equilibrium that satisfies both corporate parameters, they autonomously execute the transaction.
The agreement is codified into a smart contract on a distributed ledger, and the financial settlement occurs instantaneously via programmable cryptocurrency pipelines. The entire transverse workflow, from shortage detection to global negotiation to final settlement, executes over a weekend, while the human staff is offline operating entirely at machine speed.
When you extrapolate that capability across millions of interconnected enterprise nodes, it fundamentally redefines the architecture of a global market. Traditional corporate banking infrastructure, B2B sales cycles, and legacy supply chain logistics are completely bypassed by swarms of negotiating algorithms communicating via JSON payloads. As systems engineers and architects of digitalization, the ultimate challenge will not merely be building these agents to operate within our own firewalls. The profound engineering challenge of the next decade will be designing the macroeconomic guardrails, the intersystem trust protocols, and the global circuit breakers necessary to stabilize a sprawling autonomous economy operating at the speed of light. Thank you for taking this deep dive into the architecture with us. Keep analyzing the systems, keep questioning the frameworks, and we will catch you on the next exploration.